Now today we will go over QuickSort. So QuickSort is a divide and conquer algorithm, just like our merge sort. So what it does is it picks a element as a pivot and it partitions, that means divides, the given array around the pivot into sub-arrays. So this is dividing our problem into sub-problems. These sub-arrays are then recursively called to sort the elements. Okay. Let's say, for example, we have our array, -1, 1, and 0. And let's say that our pivot is the last element. So what we're going to do is we are going to have all the smaller numbers on the left side. So any number smaller than 0 is going to be on the left. So that's going to be -2, -1. And all the numbers greater than our pivot is going to be on the right. So 1 and 2. And 0 is going to be on our sorted list. And I just kind of sorted the rest of the elements, but that may not be the case. But when we do this, we know for a fact that this one number is in correct position. And we recursively run our quicksort on this left one and on this right one. And we keep sorting our elements. So that's the basic idea of quicksort. And there are many different ways to pick our pivot, and regular or normal implementation is where we pick the last element as our pivot. And there are of course different ways, which is first element as pivot, middle number as our pivot, and a random number as our pivot. And we are actually going to implement all these three using different methods. And remember, QuickSort is a divide and conquer algorithm. So divide. The array is divided into sub-arrays at the pivot. And this is what we saw, right? The left side and the right side. Elements smaller than the pivot are placed to the left. Everything is smaller, while the greater numbers are on the right. And then we conquer. The left and right sub-arrays are again partitioned at the pivot. So what does that mean? Well, it means that this left side is going to have another pivot, which this time is going to be -2, and right side is going to have another pivot, which is going to be 2. And we just keep running our quicksort recursively. And finally, we combined. And for our quicksort, it doesn't really apply because the array is already sorted at the end of the conquer step. It should be of. The work is done while dividing the array into sub-arrays. So we actually combine our result as we run our quicksort, and you will be able to see that later. Now, this method that we went over is actually called Lumoto's method, where we have to choose a pivot that is typically the last element of the array. So this is a typical solution for quicksort. So last element as the pivot, an element in the left half are smaller than the pivot, and the elements to the right are greater than or equal to the pivot. So for this one, we only have one pointer that kind of tracks which numbers are greater than or smaller than our pivot. And the second method, which is called Hoare's method, it has two indices that start at both ends of the array. So if we have our array, we would have 2 for our Hoare's method. So it would look at -2 and -1 as we compare our elements and see if it's smaller than or greater than our pivot. And I'll illustrate this in more detail for both of them after this. So both ends of the array being partitioned, which is moved towards each other until inversion is detected. Meaning if they're out of order, they're going to be swapped later. The inverted elements are then swapped, okay? Unlike Lumoto's partition, the pivot element is not excluded in subsequent recursive calls. Okay, this is the important part. Remember that for our short, small example, which is not very representative of Lumoto's method, what we did was we excluded the 0 when we kind of sorted our array. When we had elements left smaller than the pivot on the left and elements greater than on the pivot on the right. But Hoare's method is not going to exclude that pivot number. It's going to include it. And the reason is because Hoare's scheme is more efficient than Lumoto's partition because it does 3 times fewer swaps on average. So Hoare's method is actually faster than Lumoto's because it does 3 times fewer swaps. And apparently, so I was looking up difference between Lumoto's and Hoare's, and I was wondering, why can't I take the pivot element out when I'm using the Hoare's method? But apparently, if you do that extra work, it makes it slower. And I will mention that again later. but just know that if we do that, it's slower in general. Now, let's go over our time complexity just briefly. It's going to be O log n because of partition of our arrays, because we are dividing our arrays and we are doing O of n comparisons per partition. And this is pretty much same as our merge sort, right? And best is n log n, average is also n log n, and worst is n squared. When the pivot picked is the maximal or the minimal element, this is when the pivot element is at the extreme end of the sorted array. One subarray is always empty while the other contains n-1 elements, and quicksort is called only on this subarray. So it would be something like when there's 0 elements, there's nothing in the left, and this is the pivot, and all the rest of the elements will be over here. So that's the worst case. And space is O log n because we need extra space for our stack frames. If you guys find this helpful, make sure you guys like and subscribe. Thanks. Now let's go over our first illustration, which we are going to use Lumoto's method, and this is the most typical method that you will see for quicksort, but this time we are actually going to use the first index or first element as pivot. Well, typically it's usually the last as pivot, but just for fun, we will use first as our pivot for this illustration. So we have this as our array, and as we said before, first one is going to be our pivot, so that's going to be 3. And we are somehow going to sort this so that everything on the left is smaller than 3, right, is greater than 3. And for this method, we are actually going to have 2 pointers, well actually 1 real pointer and 1 to just iterate through our array. And let's say our P is equal to our partition index, and I is going to be our loop as we iterate through our array. And let's have our partition index start at 3, and our I is going to start at 4 because, well, 3, do we have to look at 3? Well, it's pivot, so we don't really have to look at 3. That's why. So as we go through, what we're going to do is we are going to check if our current element, which is represented by I, is smaller than our pivot. Okay, so let's start. So first iteration is 4 less than our pivot. Well, our pivot is 3, so that's false. So what we do is we move our pointer, and that's going to give us partition is going to stay the same, and pivot is always going to be the same, and our I is going to move to 1. And now we check, is our current element smaller than pivot? And I actually made a mistake here. Our pivot should be moved to here. My current element is 1. Is that less than my pivot? Well, that's true, right? So what we do is we swap these two, and that's going to give us this as our array, and our I is going to be here, and our partition index is going to be here. And now we check again. Is our current element smaller than the pivot? 1 is less than pivot, so that's true. So we swap again. So 3, 1, 1, 4, 2, 5, 0. And where is our I going to be? Where I is going to be here, and our pivot is going to be pretty much here. And we check again, is 2 less than our pivot? Well, that's true. So what we do is, again, we swap, and now our I is going to be here, and our P is going to be here. And we check again, is 5 greater than our pivot? Which is false. So we continue on. We don't swap anything. Now our I is here and our pivot is pretty much here. And then we check again. 0 is smaller than pivot, which is true. And then we swap. And as you can see that all the numbers to the right are greater than our pivot. All the numbers to the left are smaller than our pivot. But we are actually not done yet. What we do last is we swapped these two numbers. And as you can see, we were able to separate our array into 2 subarrays, left and right. And we recursively run our quicksort function on the left and on the right. And remember, under Lumoto's method, we exclude the pivot. So we won't include that in our next quicksort. So this is pretty much an illustration of our quicksort in Lumoto's method. And we use first element as our pivot. So keep this in mind. And well, just one more thing. If you were to use last element as the pivot, it's pretty much the same we're just gonna start here. Well, we're just gonna use 0 as our pivot, and we are going to do the same. Compare 3 and 4, and so on and so forth. And similarly, we are going to have our sorted array, but for this one, it's a bad example because 0 is the smallest number here, so we will have to do comparing everything. So that's it for illustration for Lumoto's method. And now let's get to our first solution. Let's go over our first solution, and like I said, we are going to use Lumoto's method, and we are going to choose last element as our pivot. Now I have my pseudocode, and you can read it and try it on your own if you like. If not, you can come back to the video and we will go over the whole thing. Now I want to go over our pseudocode for the first one because I think it's just helpful. I think it's going to solidify the concepts of Lumoto's method really well. So first thing we do is we are going to create a function that takes in 3 parameters. And first one is going to be array, which is our original input array. Next is our start, which is going to represent our first index of the array. And end is going to represent our last index of the array. And we are going to create our usual swap function. And I just wrote that over here because we did that too many times. And next, we are going to create our partition function. And this is pretty much what does all the work for our quicksort. It compares and sorts our element. Think of our partition function as our merge function that we have for our merge sort. And if you remember from our merge sort, merge is actually the one that did all the work. So comparing, sorting, and merging all the elements. And like our merge sort, partition function will compare and sort our elements. And this will also take 3 elements or parameters actually. And first one is going to be array. Next one is going to be the first index of our subarray, and next one is going to be last index of our subarray. Well, if you remember from our illustration, when we did our first operation of quicksort, we noticed that 3 ended up here, and we had 5 and 4 on the right, and then rest of the numbers on the left. So for example, let's say that we are looking at all the elements on the left, and if you were to pass in this left side of the array, we actually don't slice only this part of the array. We actually pass in the whole thing, pass in the whole original input array. It's just that we give 2 indexes so that it only looks from index 0 to index 3. So in a way, we are kind of slicing our array, but we do that with our indexes. We just make our function, our partition function, only look at this part by designating left and right indexes. Next thing we are going to do is we are going to store our pivot point, and for this one obviously it's going to be the last one. Next one is our pointer variable that will be used to compare and swap our elements, and this is going to be the partition index of our subarray. And if you remember that we use variable p for our illustration. And next we want to iterate through our subarray, and we compare if our current element is less than the pivot, and if that's the case we can just swap. And again, you don't really need this if statement, you can just swap if you like, and then we increment our pointer variable by 1, so our p index by 1. And finally, we do that last swap. And again, if you remember from our first illustration, we sorted everything, our 3 ended up being here, and then the last swap put our 3 over here and I think 0 over here. So we had 0, 1, 1, 2 on the left, 3 as our pivot, 5 and 4 on the right. And finally, we return our partition index. Next, we need a base case for our recursive function, and that's going to be if start index is greater than or equal to end, we are going to return. So that means that pretty much we went through all the items in our array, and we are actually going to declare a function, and we are going to save our partition index by running the partition function, which returns a partition index. So we save that to a variable, and we recursively run our quicksort on the left side and the right side. And finally, we return our sorted array. So that's it for our pseudocode, and I thought it was good to go over it just once because we can kind of go over the concept one more time, just step by step, and just solidify things that we know. And I will actually go over our pseudocode one more time when you use Hoare's method. But for now, let's leave it at that and start coding. So I have my function, I have my swap function. Next thing I want to do is I want to create my partition function. So const partition, and that's going to take 3 parameters, which is going to be array, the first index and the last index of my subarray. And the next thing I want to do is I want to create a variable, and this is going to save the pivot. And let's just call it pivot, and this is going to be the last element of my subarray, so index r. Next, I want to create my key index, the partition index, and set this equal to the first item in my subarray, which is represented by L. Next thing I want to do is I want to iterate through my subarray, which starts at L and ends at R. So for let I is equal to, well, it's not going to be 0 because my subarray isn't always going to be starting at 0. So it's going to start at index of L. And we want to iterate through the whole thing until I is less than R. And remember, we don't have to iterate to the last element because last element is always going to be a pivot for this specific solution. So we can just leave it at that. But other case, you might have to change where I starts and where we loop until. Just know that, and actually this will change a little when we start with a pivot as our first element. But for now, let's just leave it like this, and let's increment by 1 each time so that we go over all the elements in our array. And next, we need to compare our current element to our pivot. So if our array at index I is less than our pivot, what do? We swap. We pass in the array, we pass in the current index and the pivot index. And again, if you remember from our illustration below, before compared our current element to pivot, and if that was the case, we swapped using the current index and the pivot index, which I just wrote as P before. So that looks good, and we actually need our final swap, and that's when everything else is sorted except for our pivot. So what we do is we swapped it with our pivot index. So that's going to be swap array p index. And what do we put as our other index? Well, it's going to be R, because for this one, we are using the last element as our pivot, and we want to put this last element to its correct place where it should be. So that's represented by p index. And finally, I want to return my p index. Okay, that's actually it for our partition function. Now we need to handle our base case for our recursive function. So if start is greater than or equal to our end, we are just going to return. And now we need to save our partition index to a variable. So const, I'm just going to call this p index also, and I'm going to run my partition function and pass in my variables, array, start, and end. Okay, that looks good. So what I'm doing here is I'm running this partition function, passing in these variables, and I run this whole thing, I sort it, and I do my stuff, and finally I return my partition index, which is going to be saved to this variable. Now I need to recursively run my quicksort function. So quicksort and array start index, and then my ending index, which is going to be p index minus 1. Well, you might be asking, why is it p index minus 1? Well, the reason is because according to Lumoto's method, we want to exclude our pivot, and that happened to be over here, if you remember from our example. So when we recursively run our quicksort function, we want to look at everything to the left, which is this one. So start to p index minus 1. So since this was the p index, we look at all of this and all of this. So this one, the first one represents the left side, and the next one is going to represent the right side. We run quicksort again on the right side. So same as before, p index, but this time is going to be +1 and end. Well, it's the same reason, because if we were to just write p index, that would include this element also, but we want to look at only the right side of our partition index. So that's why we do +1 on the right and -1 on the left. But just one thing, for our Hoare's method, which we will go over later, it's going to look different. Just keep that in mind, but I'll explain more about that later. And finally, we just return our array. And I actually skipped one thing. I forgot to increment my partition index. That's why we've been getting a wrong result. So if I were to increase my partition index, you will see that everything's sorted. I hope you caught that error, because if we don't change our partition index, it's always going to be the first element, which is represented by L. So it would be just swapping numbers in this index only, and that's not really going to change anything, right? So I hope you caught that mistake. So as you can see, our results are all sorted. It handles negatives, duplicates. This is just an array with random numbers, which seems like it's sorted. So that's it for our first solution. And remember, this is using Lumoto's method, and we picked our pivot as the last element. Now let's go over our second solution. And for this one, we are going to pick first element as our pivot. And we have our pseudocode, which is pretty much like 99% exactly the same as our first solution, which used last element as pivot. But this is a pseudocode. You can take a look and try it on your own, and if you can't, come back to the video because we will go over it. Now, same as before, I have my quicksort function and I have my swap function, and next thing we need is our partition function, and that's going to take three things: array, the left starting index, and the last starting index. Next, I'm going to declare a variable and call it pivot, and this time it's going to be the first element. And same as before, I'm going to make my pivot index. That's going to be p idx, and we are going to set this equal to L also. So the first one. Now I'm going to iterate through my array and start at index I is equal to L plus 1. Well, why is it L plus 1? Before it was, when we used last element as our pivot, it was just L, right? Well, it's because since this element is going to be our pivot, well, do we need to compare 3 to 3? No, right? It's the same exact element on the same spot. So we skip that, and that's why we start at index L plus 1. So we are going to iterate until I is less than or equal to R, and increment by 1 each time. So our for loop's a little different. It starts at index I plus 1, and we went over that, and that's because 3 is our pivot and we don't need to compare pivot to pivot, and our condition is different. Before it was I is less than R. Well, the reason is because before, when we chose last element as our pivot, do we need to check this? Well, it's the same reason why we are not checking 3, right? But this time we need to check over to our last element. If we were to just leave it like this, our for loop would end when we hit our number 5, and we don't want that. We need to compare our last element also. So we can just do R plus 1 or I is less than or equal to R. So that's totally up to you, but I think this is more intuitive, so I'll just leave it like this. And we need to now compare our elements. So if array at current element is less than our pivot, we want to swap, right? But unlike our first solution, what we have to do is we have to, for this one, increase our pivot index first. So that's going to be p idx plus plus, and we swap. And we pass in I and p index like before. Okay, that looks good. So we are going to be swapping all our elements except for the first one. And we want to handle that here when we are done with that. So swap array. And this time it's going to be what? It's going to be RL and pivot index. And finally, we return our p index. All right, that looks good. And our recursive function is pretty much the same. So if start is greater than or equal to end, we return. So if you iterate through the whole thing, we just return. Then I'm going to save my partition index to a variable, and I'm going to run partition, pass in my array, starting index and ending index. Now I just need to recursively run my function. So quicksort, pass in my array, start at index start, and p index minus 1. Because again, we want to exclude our pivot. Again, it's the same thing, array, p index plus 1, because again, we want to exclude our pivot, and end. And finally, we want to return our array. And as you can see, we have our final result. So starts at 0 and goes all the way to 5 in order. And this is our array, handles negatives and duplicates. And this is our random array, which seems good. So this is our QuickSort in Lumoto's method using first element as our pivot. So everything else was the same except for our this part. So that's it, and we will go over Hoare's method next. Now I just want to go over the difference between our two first Lumoto's method, where we used pivot as last and pivot as first. And if you remember from our solution, only thing that differed is pretty much the partition function, especially where we have our for loops and how we increment our pivot index. So let's look at our first solution, which was where pivot was the last one. And if you remember, our pivot and our index started at the same place, right? And that's because our pivot point was the last element. So now we were doing our checks as we were iterating through our array. And remember that we had our P set to L, our partition index, and I started also at L. And we iterate through all the elements till we hit 5. We don't need to iterate through 3 because 3 is the same exact number at the same position as our pivot. Now we check, is our current element less than pivot? So that's false. So we increment our I by 1, which now ends out at 4. Now is 4 less than our pivot, which is false. So we iterate through our next element, which is 1 over here. And now we check, is 1 less than our pivot? Well, it's true, right? So what we do is we swapped these two numbers and we have 1, 4, 3. And remember that we increased our pivot after we swapped. So now our pivot ends up here. Now we check again, is our current element less than our pivot? Well, it's true. So we swap again. And after we swap, we increase our pivot index. But if you were to do that before swapping, so if you were to increase our pivot index before swapping, our pivot would be here and we'll be swapping 1 and 3. That would be totally wrong, right? So we swap 1 and 4 and we get 1, 1, 3, 4 as our result. And we look at our next element, which is 2. Is 2 less than our pivot? Well, that's true. So what we do, we swap again. So now we have 1, 2, 2, 4, 3, 5, and the current element is at 5. Is 5 greater than pivot? No, it's not. So we just stop there because again, we don't need to check this. We stop here because that's our pivot. So last thing that we have to do is we have to swap pivot with our pivot index. So if we were to do that, our final array will look like this over here. So our pivot ended up being here, and everything to the left of it, it's smaller than our pivot, and everything to the right of it is greater than or equal to our pivot. And we recursively run quicksort on this one and our left side of the subarray. Now let's look at our next one, which is when pivot is first. I know that we went over this, so if that swapping didn't confuse you, if that having different conditions didn't confuse you, you can just skip this part. So for our last, we swapped after. Here we swap before. Or let's just put it this way, P index plus plus after. I think that'll be more intuitive. So here we did P index plus plus before. And for our for loop, I starts at L and I is less than R. And for here, I is L plus 1 and I is less than or equal to R. Okay, now let's look at our next example. And for this one, we start at index L plus 1. Well, what's the reason? Because the reason is because our first element is our pivot and we don't need to check that. It's the same exact element at the same exact spot. Now we check, is 4 less than our pivot? Well, that's false. So we increment our I by 1, which ends up being at this one. Is 1 less than our pivot? Well, it's true. But remember, we have to increment our P index by 1 before swapping. Say that we were to do that after swapping. So that means that we have 1, 4, and 3. And remember, we don't want to move the position of our pivot until we are done with our first iteration. So that would be wrong, right? So that is the reason why we increment our pivot index by 1 before. And then we check again, is 1 less than our pivot? Well, that's true. So we increment our pivot and then swap. So we have 3, 1, 1, 4, and then our current number is going to be at over here, which is going to be 2. Is 2 less than our pivot? Well, that's true. So we increase our pivot first because this is true, and then we swap. And then we have 2 and 4. Next, our current element is 5, and is that smaller than our pivot? No. So we increase our I again one more time, which it ends up being at 0. And is 0 less than our pivot? Well, that's true. So we increment our pivot index first because it was true, and then we swap these two numbers and we get this as our array, and our final swap is going to be our pivot index with pivot, which was first element. So we swap these two and end up with our somewhat sorted array for the first iteration, where we have 3 as our pivot and all the elements to our right is greater, elements to the left are smaller, and we recursively run quicksort on these two and then slowly sort our array out. And remember, we have our I is less than or equal to R because we want to hit this last number. If we didn't have that, if it was just I is less than R, we wouldn't check this number and it would be wrong, right? We would have 0 here and I would be here, and that wouldn't make things work. It wouldn't be sorted the way we want it to be. So that's why we have to hit that last element. So this is pretty much the difference between first pivot and last pivot. I hope this helped, because just seeing it like this, it just makes so much more sense. I mean, if you can see that without illustrations, that's great, because I had to really write everything out for me to really understand it. But this is it. Well, I guess the biggest point is that, remember, the pivot index is always behind our I, and that's the case for both of our illustrations. So that's it. I hope that clears some stuff out. Now let's go over how Hoare's method work. So for this one, we are going to choose the middle element as our pivot. So it's going to be number 1. And we are going to have 2 pointers. One is going to be the first element and one is going to be the last element. So ends of the array. So we have points at the 2 ends of the array represented by L and R. So what we do is we check if our element at the left index, so is left index smaller than our pivot value, and we check if our right is greater than our pivot value. Well, this makes sense because we want all the elements to the right to be greater than our pivot and all the elements to the left to be smaller than our pivot. So what we do is we check, well, what's our L and R value. Our L is 3 and our right value is 0. So is 3 less than pivot? No, that's false. Is 0 greater than pivot? No, that's false. That means that they're in the wrong position relative to the pivot. So we swap those two numbers. So these two numbers. So it's going to be 0, 4, 1, 5, and 0. And our pivot is going to be here. And the left index is going to be here. And right is going to be here. And then we check again. Well, is 4 less than pivot? Well, that's false. Is 5 greater than pivot? Well, that's true, right? So what we do is we just move the right pointer until we find elements that's smaller than our pivot. So that's going to yield us same array. We are going to have the same position for our left variable and same pivot, but our R variable is moving to the left. And we check again. Well, is 2 greater than our pivot? Well, it's true again, right? But just one thing, we don't have to kind of check this one because it's down here. So we move our R variable one more time. And you can see that our R moved to the left one more time. So L is moving to the right and R is moving to the left. And finally, our 1 is greater than pivot. Well, that's false. So we swap. And if you notice, we swap when both elements are false. So that's going to yield us this array, and our pivot is going to be here. And if you notice, our L and R is going to be here. So we actually stop out of this whole operation when L is less than or equal to R, and we hit that over here. So we exit out of our operation. And as you can see, elements to the right are greater and left is smaller. And we split our array into 2 and recursively run our function on these 2 arrays. But one thing that you have to keep in mind is that when we use Lumoto's method, we excluded what? We excluded our pivot. But for Hoare's method, we keep it. we run the quicksort with that pivot variable. And I mentioned in our intro video, well, theoretically, well, this is what I thought. If I can exclude extra number that have to loop through, isn't that going to be faster? Well, apparently it's not, because we have to do that extra swap. Remember that for our Lumoto's method, when we were done with our looping of the whole array, we had to swap our pivot with the partition index, right? So apparently that takes a lot of work for the computer, and it actually makes it slower if we were to exclude that number. So just know that, and that's something that I read researching. But what I will do is I will actually implement a method later that does Hoare's plus Lumoto's method combined. So I'm going to use two index plus exclude partition just for fun. And last thing I do want to mention is that Hoare's method is around 3 times less swaps than Lumoto's. And this is also something that I read in a paper. I think if you research Lumoto versus Hoare's, I think you should find it pretty easily if you want to read more to it. But that's it for Hoare's method. And now we will get to our solution. Now let's go over our Hoare's method, and for this one we are going to use the middle element as our pivot. So as for Hoare's method, so the process is pretty much the same except the fact that we are going to use two indices like our illustration, and other than that the pseudocode it's exactly the same. We have our function which takes in exactly the same parameters, and our base case, our recursive case is going to be the same. It's just that our partition function, which is in charge of comparing and sorting our elements, it's going to be a little different. So this function, like before, is going to take an array, left index and a right index. And of course, like before, our array is going to be the whole array, but we are only going to look at this first and last part, which is represented by these two indexes. So in a sense, we are looking at a part of our array, and we are going to be performing operations on that only sub-array. We are going to make our variable pivot, and we are going to make it to our element, and we will round down, and we will iterate as long as our left index is less than or equal to our right index. And if you remember from the illustration, when this condition happens, that means that we iterate through all the elements in our array. Next, I want to iterate through my array starting from the left. So if my element at left index is less than the pivot, I'm going to increment my left index by 1. And if it's the other case, if my right element is bigger than my pivot, I'm going to decrement by 1. Well, if you remember, we swapped items when both of these statements came to be false. So if my statement is false, that means that I have an element that's bigger than my pivot on the left side, and obviously I want it on the right side, right? And same thing goes for my second condition, which is r is greater than my pivot. If this is false, that means that I have an element on the right side that's smaller than my pivot, so I want to swap those two. And we check, well, is left less than or equal to r? If that's the case, I want to swap, and we increment our left index by 1 and decrement our right index by 1. And finally, we return our partition index, which is going to be represented by L. And I'll explain why this is so, why I wrote return L and comma partition index. So just to give you a hint, our L, our first index of our sub-array is going to be working like our pivot index. So now everything else again is the same. Try it on your own if you can't. If you can't, come back to the video because we will go over it. Now let's start coding. So first thing I want to do is I want to create my partition function. This is going to take 3 parameters, array, left and right. And next I want to create a variable to store my pivot. And pivot is going to be our middle element. So array at index. So we want to round down. It's going to be L plus R divided by 2. Okay. Now we need our while loop. As long as my left index is less than or equal to R, I want to iterate through my array from the left side and the right side. So if my current element at left index is less than my pivot, I want to move through my array to find the element that's greater. So I want to increment L by 1. Now I need the other case where array at index R is greater than pivot. If that's the case, I want to move to the left. Now it's our swap. So if L is less than or equal to R, what we want to do is we want to swap. We pass in our array, left index, right index, and after we make our swap, we want to increment our left index so that we can check on our new elements in the array, and decrement right by 1 because we want to move towards the left. And finally, I want to return my L for pivot index. And if you remember, for our other solution, we used variable called p index, but here I just use this one because it works for this specific solution. So what I could have done is, well, we know that we need 2 pointer variables for our Hoare method. So what I could do is do something like, let's do L is equal to left and let R is equal to right. And I can just rename this actually to this, and it will work the same, but I can just use L to do the same thing. I think it just makes the code a little shorter, so I'll just keep it. But if you want, you can just get rid of that and let's just change this back. And finally, our base case, the start is greater than or equal to end. That means that we iterated through all the elements and did all the necessary swaps. So we're gonna return, and I want to save my partition index. And this is going to be equal to, we are going to run the partition function, and we pass in the array, start index, and the end index. Okay, so that looks good, and I spelled partition wrong. Now we need our recursive case, so we'll call QuickSort, pass in our array, pass in our starting element or starting index, and pass in our ending for our left half. And if you remember, this one looks exactly the same as our Lumoto's method where we exclude the pivot itself. But for this one, on the right side, is going to be different. We are going to pass in array. We are going to pass in p index and end. If you remember, for the other methods, we added 1 here so that we can exclude our pivot. But remember, the definition of Hoare's method is that we want to include it, because in the end, it happened to be that even if we excluded this pivot, the extra last step of swapping the number actually made our, I guess we can call it code slower or operation slower. And finally, we want to return our array. And as you can see, we have our answer. So this one's sorted, our array with random numbers are sorted. So this is it for Hoare's method, and our pivot is the middle element. Our recursive case and our base case was pretty much the same. Only difference was that our pivot function was different. So we create our pivot, we iterate through our array as long as left index is less than or equal to right index. If this is false, that means that we iterate through all the elements in our array and we did our necessary checks and swaps. And this first while loop is looking for a number that's greater than pivot so that we can move it to the right side. And that's increasing index by 1 each time to find that number that's bigger than our pivot. And this one is starting from the right side, looking for a number that's less than the pivot. And if these two while loops becomes false, that means that we found a number that's bigger here and smaller here. So we check again, is this done looping through the whole thing? If not, we are going to swap those two numbers and we increment the left index because we want to go towards the right, and decrement right index by 1 because we want to go towards the left. And finally, we return our pivot index. And remember, I said that you can just make a specific separate variable if you want. So just uncomment these and change this to left and right, not L and R, and it should work the same. Now I want to go over our Hoare's method using a random element as pivot. And this one is going to be exactly like 100% or 99% exactly the same as our Hoare's method where we use middle element as pivot. So only difference obviously is going to be our pivot, how we get our pivot. So I didn't bother coding the whole thing out from start to beginning because again, it's going to be exactly the same. And if you were to just look at our result, everything seems good, right? Everything's sorted. So only difference is this line where we find our pivot. So all we did was we round down, we get a left number, and we multiply by r minus l. So the last index minus l plus 1, and we added l to that. And if you were to test this out, you would get all the numbers in our solve array. So you can test it on your own, see what you get, and I don't think you should have any problems with it. And the logic itself is the same as our Hoare's method where we use middle index. So this is it for random pivot. Just know that this line is the only difference that we are going to have. Now let's go over where we implement our solution using both Lumoto's and Hoare's method, and this time we are going to use the last element as pivot. But remember, this extra step that we use for swapping our pivot at the end makes this overall slower than Hoare's. But let's just try this out just to see how it goes. Again, this is going to be combinations of Lumoto and Hoare's method, and you can read the pseudocode to try it out. But I think we did enough of QuickSort to be able to implement it on our own. But do know that this is going to be a little different than Lumoto and Hoare. Now let's go over our code. So as always, I'm going to make my partition function, and that's going to have 3 parameters. First one, array left and right. First thing I'm going to do is I'm going to make my pivot and set this equal to array at index right. So it's going to be the last element. And I'm going to make 2 variables. So let L is equal to left and let R is equal to right minus 1. And you might be saying, why is it right minus 1? Well, it's because if you were to set our last element as our pivot, we don't have to check that one. Now let's make our while loop. As long as L is less than or equal to R, we are going to do the same thing. So pretty much Hoare's method, array L is less than our pivot. We want to increment our left index by 1. We want to move towards the right. And now we need the other case. Array at index R is greater than our pivot. We want to move towards the left. And if L, our left index, is less than or equal to our right index, we want to swap, pass in our array, and pass in our 2 indexes. And we want to increment by 1, and we want to decrement by 1 to move towards the center. Now, the major difference comes from this line, and this is where we swap our element. And this comes from our Lumoto's method, because remember, we want to swap this number or the pivot to the point where we partition our array. So all the items to the left is going to be smaller, and all the items on the right are going to be bigger. So we pass in our array, and we pass in our index, pivot index, and we pass in our right. Because why is it right? Because this is where our pivot is. We haven't moved our pivot, unlike our Hoare's method. Pivot stays at the same like Lumoto's method. So we have to swap at the end. So if you look at our Lumoto's solution, you will see why we did this. And it's the same reason why we do this. We want to move our pivot to the correct place. And finally, let's return our pivot index. And our base case is going to be the same. So if start is less than or equal to end, so when we iterate through all the elements, we just want to return. And now we need to find our partition index. So const partition index is equal to, so we call partition and pass in our array, starting index and ending index. Now we need to handle our left side. So let's call QuickSort, and we are going to pass in our array. We pass in our starting index, and then we pass in our partition index minus 1 because we want to exclude pivot element, and we call QuickSort on the right side. So array, and this is going to be pivot index plus 1 and ending index. And finally, we return our array. And again, I spelled partition wrong. Okay, now if you were to check our results, our arrays look good. They're all both sorted. So the first array, the array with negative numbers and duplicates, a random array with 10 random numbers, they are all sorted. So it's a lot like a combination of Hoare's method and Lumoto's method, right? So this one comes pretty much from Lumoto's. This one comes from Lumoto's. It's exactly the same line. This one, it comes from Lumoto's. But everything else, this whole while loop, it's coming from our Hoare's method. So that's it for our combination of two methods, but just do keep in mind that this method is actually slower than Hoare's method, and part of the reason is because of this one extra step, this swap. So apparently this makes our whole code slower than our Hoare's method, but I think this is just a good solution to code just for fun, just to test your understanding of QuickSort. And that's it for this solution. Now, this is actually going to be our last solution. And this time we are going to optimize our code just a little bit. And remember that Hoare's method is faster than Lumoto's method. So we are going to use Hoare's method plus insertion sort. And we are going to make the middle element as our pivot. Well, why do we have to use insertion sort along with QuickSort? And if you remember, or if you know, QuickSort, just regular QuickSort, really works well with bigger arrays, and insertion sort is faster for smaller arrays. And when you use the sorting function within Chrome, what happens is it uses QuickSort, and when the elements are less than 10, it uses insertion sort. So we want to try implementing that solution, and this is the pseudocode for it. So to be honest, if you remember, insertion sort is exactly the same thing. It's just that it's going to take a few more parameters because it needs starting and ending index, because we are going to pass our sub array into our insertion sort. And other than that, our Hoare's method is going to be exactly the same. So this is the whole pseudocode. You can try it on your own if you like and come back to the video. Now, this is our solution for QuickSort using Hoare's method along with insertion sort. And I just coded everything because I think we should know how insertion sort work. We went over that last time, but the only difference is that it's going to have two more parameters, which is going to be start and end. And remember, insertion sort is going to be run on our sub arrays. So that's why we need this. And it's going to start at start index 1, and then it's going to iterate through all the elements. So it's going to be I is less than or equal to end. And I'm actually skipping a lot of stuff because we went over this. And then we are just sorting our array, our sub array with insertion sort here. And I have my partition function, which is exactly same as our Hoare's method. Literally nothing changes. It's exactly the same. Only difference is going to be over here. And it's this if statement. So if ending index minus starting index is less than 10, we are going to run insertion sort, and we are just going to return that array. So this is pretty much the only difference, and this is the condition where insertion sort is going to run. So if our sub array is less than 10, we are going to run insertion sort. That's it. Otherwise, we are going to run our QuickSort, regular QuickSort, and Hoare's method to be exact. And so overall, this is optimized as faster because insertion sort is good at handling smaller arrays. And if you look, we have our array which is all sorted, and I have an array with random numbers, 100 random numbers that ranges from -100 to +100, and as you can see, they're all sorted really nice. We have a lot of duplicates, positives and negatives, and no problems. So this is it for our QuickSort, and let's wrap it up with time complexity. Now let's go for our time complexity just one more time in more detail. Well, the O of log n comes from partition of arrays, and this is a log n operation. We are having the number of operations each time, and we are doing O of n comparisons per partition. And best case is n log n, because when pivot element is the middle element or near the middle element, there is less swaps to do, and this is when elements are mixed. And worst case is actually O of n squared. Well, that happens when the pivot picked is the highest or smallest value in our array. So that means that if you were to choose the smallest number as our pivot, that means that we are going to have any elements on the left. So we are going to be recursively calling the rest of the array, so n minus 1 elements on the right side only. And if it's the case that our pivot is the highest, it would be the opposite. So that's why it's going to be O of n squared. And our space complexity is O of log n. Why? Because we only need space for our recursive calls and nothing else. It's not like we created an extra variable to store our sorted element. We did not need that. We just used in place method instead of creating a auxiliary space for our space complexity. So this is it for QuickSort, and I know that this was way longer and probably harder than other sorting algorithms, but I think this is really good practice overall, just exploring different options. If it really confuses you, just take away one thing, and it's the first solution that we did, which is Lumoto's method using the last element as our pivot. That's the usual implementation of QuickSort, but here we went over Lumoto's, Hoare's method. We combined these two methods, and we used insertion sort along with Hoare's method, which is used in Chrome's sorting function. So that was really interesting. I hope you guys learned a lot from this one.